In our physics labs this week, we were given a Lego dart cannon, and we had to fire the dart accurately enough that it hit a target at a given distance. The catch was we could not run any tests on the dart apart from firing it vertically, so we couldn't fire it horizontally. But as an added incentive, we were promised muffins if we hit the target. So the first question was, what exactly were we trying to figure out? We knew the distance, but we didn't know the angle to set the cannon so that it hit the target. To do this, we needed to work through the physics. So we thought about how it would look if the dart was fired horizontally. It would move across the floor while initially going up and then falling to the ground. The horizontal distance it traveled would be related to how long it stayed in the air, because gravity is assumed to be the only force acting on the dart, pulling it down. So the horizontal speed is assumed to be constant. That is, it would only travel horizontally as long as it was in the air. So using the time it spent in the air and knowing the initial horizontal velocity, we could calculate the distance it traveled horizontally. So the next question was, how could we characterize the dart if we could only fire it vertically? For that, we had to think about energy. Energy is the capacity of an object to do work on another object. Before the dart is fired, the coiled up spring inside the cannon had some stored up potential energy because the spring is compressed and held in place until we fire the cannon. When we fired the dart, this energy is transferred into the dart and gave it kinetic energy, which exists because of the dart's motion. The dart would then reach a maximum height and then fall back to the earth. So when the dart reaches the maximum height, all of its kinetic energy changes back into potential energy. But this potential energy is because of the separation between the earth and the dart. And when it starts to fall back to the earth, that potential energy changes back into kinetic energy. So, knowing all of this, how could we use this to figure out the angle we needed to set the dart? To understand that, we had to work through a bit of math. When firing the dart horizontally, it would travel across and up initially. We can set an angle, theta, for the cannon, and we can find the initial velocity v. Using some trigonometry, the initial horizontal speed, which would be cosine theta times v, and the initial vertical speed would be sine theta times v. So, the time taken to travel across the floor would be the time taken to rise and then fall. That would be the vertical speed divided by acceleration due to gravity, because gravity is pulling it down, times 2, because it has to go up and then come back down. Next, we found the horizontal distance. Knowing that speed is equal to distance by time, distance would be speed times time, which would be cosine theta times v times 2 times sine theta times v divided by g, which we got earlier. Now we needed to fill in our blanks a bit, using our knowledge of energy, because we could only fire the dart upwards and could not really measure the initial speed, so we had to find another way to fill in our earlier equation for distance. We knew that potential and kinetic energy are linked. The maximum potential energy of the dart when fired upward, when it reached its maximum height, would also be equal to the maximum kinetic energy just as it leaves the cannon. So, mgh, potential energy, is equal to half mv squared, kinetic energy. Simplify this a bit and we get v squared is equal to 2gh. Plug this back into our equation for distance and we get this. Simplify that a bit further and we find this. Now we don't even need velocity. We just needed to find the maximum height that the dart could reach, plug it into our equation for distance, and then solve for the angle theta. So this is how we set up our dart. Credit goes to the rest of my group who came up with this ingenious device that was stable enough so that we could have good consistency in the values, perform repeated tests without much effort to reset the equipment, and made it easy to use. After 8 consecutive tests, we came up with the following values. 2 results were discarded as they were largely out of range, possibly due to some flaw in the mechanism. Finding the average of these values, our final height was 1.135 meters. Using this height and the given distance of 1.3 meters, we calculated a final angle of 17.5 degrees. Using this angle, we were able to hit the target on the second try. The first time we missed because we hadn't correctly aligned the cannon with the dart along the horizontal axis. Uncertainties in the experiment included the measurement of height, which we used a meter ruler for, and the measurement of the angle, which we used a protractor for. Accounting for these, we calculated the following as a final range. Thanks so much for watching. Hope you enjoyed it as much as we did.